We know that if you puncture the skin of an airplane, that's a bad thing at 35,000 feet. And it's mainly bad because you're at atmospheric pressure, 100 kPa in the cabin, and outside it's less. It's roughly the same height as Everest, 35,000 feet versus 29,000. And so we'll look at how we could calculate the pressure on the top of Everest and how we can rationalize that. It turns out that you can't just take that single point and figure out what it is. You have to relate it to somewhere else, such as the pressure at ground surface or sea level, where we basically are now. I guess we're probably at 1,000 feet, not 0 feet. And so we'll look at how we calculate the pressure at the top of Everest. The other thing we'll look at is how we might calculate the pressures as we go in the opposite direction. As we go down from sea level in the ocean, or in the earth for that matter. I guess we could do either. There's very similar expressions. And the two only differ in the fact that the fluids that we're dealing with going into the ocean or in a swimming pool versus going up in the air are different. And we know they're different from what we talked about last time, in that we know that water is essentially incompressible. And we know that water is a liquid and is incompressible, and gases are gases. Air is a gas and is highly compressible. And so those are the two differences between those. And so it's not just an esoteric question. Okay, well, maybe it is recording, so maybe you do get it. We'll see. What else was I going to talk about? Of course, let's see. This seems kind of bizarre to me. But some people will do anything, I guess. I was looking for a different video, but this will do. Free diving, which I guess is going down as deep as you can. Usually you see it. Well, it's pearl divers is what it originated from in the tropics. People harvesting pearls by diving unaided, holding your breath. Apparently, you can hold your breath for 5 to 10 minutes. People say it's all mind over matter type thing. You just have to believe it. I'm not sure I can believe it well enough to do that. But these guys and gals are going diving in some kind of subterranean pipe. It's almost a borehole, but a very big one that takes people, and go down. So there are free diving records of people having dived down to 150 meters plus. I remember seeing in the nice speedos. I remember seeing in the news the other day that a Russian lady who's a world record holder 14 times had been diving off Ibiza in the Balearic Islands off south coast of Spain, and had been swept away by an underwater current and never seen from again, tragically. But amazing. And so you can probably guess that you know that when you go in a swimming pool, if you dive quite deep, you can feel the pressure on your ears. And so how do we calculate exactly how that pressure would change? And what is the standardized way of doing that? And so finally, it would be difficult to miss everything that's going on about Katrina these days. I think it was the anniversary either yesterday or the day before. Sadly, 1,800 people died. Apparently it was $108 billion in damage. Sandy, which came a few years later for New York, which is actually during this class. I mentioned about the guy, people wanting to postpone the exam, which was 2 nights later, was maybe $50 billion in damage. But Katrina, actually the hurricane, didn't do all that much. All the problems with Katrina came, you can see this, was when the levees collapsed. And you're talking about a not very sustainable city. New Orleans, as it sits below sea level, it's now starved of sediment because of all the controls that have been put on the Mississippi River that don't allow sediment to be transported there to replenish what's going on. It's framed by levees. It's subsiding due to oil and gas pumping. And so if you live here and it's intrinsically below sea level, then that's a bit of a problem. And so all the death and destruction was in the 9th Ward, where at St. Bernard Parish, one of the levees collapsed, either by being ill-designed or probably more correctly ill-constructed. And it's due to the fluid pressures that are applied on the outside of this, but not on the inside where it's only air pressure acting. And if you have too high a pressure on the outside, you can imagine that the force that applies will either shear it off or rotate it over. And that's exactly what happened. And that's where the tragedy was in Katrina. And so that's what we're attempting to be able to look at. So that's what we'll do today. So apparently we are recording, which is great. Whoops, I didn't mean to do that. I guess I did mean to do that. And so today this is what we will chat about. And my intention today is to purely use my own, to scribble. So get your pens out if you want. It's up to you. So fluid statistics. Well, we've made the case that we'd like to know what the fluid pressure is at a point. And what we'll spend today figuring out is how we get to this expression here. And it matters, this expression is entirely universal. It doesn't matter whether the fluid is a liquid or is a gas. This is always true. But being able to use it in some way to calculate what the fluid pressure is on the top of Everest or the bottom of the Marianas Trench differs because of this issue of compressibility. And so that's what we'll attempt to do today. And so I'm going to do my scribbling on here. So where are we? Well, welcome. I'm glad you're with me. Seems like a great class today. Week 2, period 1, fluid pressures. At a point. And their distribution. I say that because when you look at the pressure that might be on a levee, you're interested not only on the pressure that maybe exists at the bottom of the levee and the top, but also its distribution, because that integration of that is the force that might push it over. And so right now, we're only interested in worrying about it at a point. So what can we do, first of all? Well, what we could do is we could take a bucket of fluid. And we could think of that bucket as being weightless. That bucket has some height, which we'll call Z, and has some area, which we'll call A, and has some volume, I guess, which would be the product of those two. Okay. We know that the weight of that bucket would be equal to the volume multiplied by the density multiplied by gravity. And we know that that weight would be equal to the area times the height, which is the volume, the density of the fluid, has to be a liquid in this case, or I guess it could be a gas if it's closed top. And I guess the only caveat is that the bucket has 0 weight. It's a magic bucket that has 0 weight attached to it. So what we could do is, if we wanted to calculate the pressure that would be applied at the bottom of that bucket, which would be the pressure that would have to be applied to keep something up, the pressure is going to be equal to, well, the force. Let's call P a force. Let me get rid of those. You might have drawn those. But let me get rid of those and just call this P a force. P has to be equal to W. And this is a force. The pressure that's applied is equal to what? There you go. Is equal to uppercase P divided by the area. And if we do that, then we just take whatever this expression, which is W, which is equal to W over air. Maybe I'm being a bit pedantic here, but we've got it through. And it's area times height of the bucket, rho Z, divided by area. We could calculate. Thank you. Yes! There we go. Never was a mistake there. Yeah. Depth, rho G, which is the same as if we think of these as unit weight, then it's just elevation times unit weight. And so that's that. And so that's one way that we can do it. The other thing that we could do also would be to try and be a bit more sophisticated about this. And we could take 2 buckets. And if we took 2 of these buckets, we could define this direction as Z. It's actually negative Z. as we'll choose, but just let's not worry about the fact that it's the negative direction. Z for us will always be positive upwards. And if we start on the top here with a bucket that looks like this, and this is Z1, and if we have directly underneath it a bucket which has a second component of it which is Z2, then what we've already done is we've defined that the magnitude of the pressure here, which I guess this pressure we'll call lowercase p, is this and this. Actually, let's not do that. This is just general the way it's written. So this is just p. And so if that were the case, then this P1 would be this point here. And if we're now holding up a pressure P2, which we apply on the bottom, it's not too difficult to see that if Z2, this height here, was the same as this height, they're both the same, then this would just be exactly the same amount extrapolated. So if I can draw a straight line, it would be this. This would be the pressure here, and this would be P2. So it's not very difficult for you to see from this that merely by making this arrangement, we've shown that in general, in this particular case, if we want to get the pressure at a point, it's equal to the unit weight of the fluid multiplied by its depth, this expression here. So this is just P is equal to this here. And if we wanted to take the derivative of this, for instance, with respect to this, then all we do is lose this. Then we get dP dz is equal to gamma. And I'll put plus or minus before. So what we've done here is we've chosen to use this as just a positive height. You can't really have a negative height in this particular case. But what we'll find is that we're going to use this as the negative direction, and this would be then the positive direction. This is positive z. And if that's the case, then we'll find out that it actually should be, even though we haven't been very careful with our units, or our signs rather, our sign convention, it would actually be equal to the unit weight. Okay? So, we've kind of shown, hopefully, that pressure as you go down is equal to this. And one way to think about it would be if you look at this behavior here and you write this as, say, a derivative, a change in elevation with a change in pressure, because we can write this expression as a change in pressure with a change in elevation as equal to unit weight over 1, same, and a minus sign. Let's not worry about the minus sign. Oh, let's keep the minus sign. Then you could also think about this gradient here as being a unit weight and 1 unit. No different, right? We're just equating the two sides of this. This is this part, which is the horizontal axis, which is the same as this. And this is, did I do that right? Yeah, this is the horizontal axis, which is this. This is the vertical part, and this is the vertical axis, which is this. So that's fine. So this, as I mentioned before, is always correct. And so what we could do, if we wanted to, and here's our Everest example. Can everyone see my writing, by the way? Is it big enough? Is it good enough? No? No one chatty this morning? So here's Everest. And this is us. So we want to be able to apply the same thing to Everest. We could do it exactly the same, right? We could take a bucket full of stuff if we know what the pressure is here, and we think that it's going to be changing in some way as we go up, from this pressure here to some magnitude here that we don't know. We do know this pressure. Always should have labels on this graph. What's this pressure here? Which is roughly? Yeah. Is that on both screens? This is missing the left-hand. No, it's not actually. I thought it was missing the left-hand side. So, all right, okay. Hold your horses there, buddy. So, how high is revolution? Yeah, it is. Yeah. So that's about 10 kilometers, which is about 10 to the 4 meters. So if you do the calculation for this, to calculate the pressure at the top, so if you think the pressure at the top is equal to merely the unit weight times Z, then what is that? Pressure is equal to 10 to the 4 meters. It's the elevation. The density of air is equal to 1 kilogram per meter cubed, roughly. And acceleration due to gravity is 10 meters per second squared, which is about equal to 10 to the 5 pascals, which, as it turns out, is exactly the same as sea level. And so, although we can assume that this expression is true everywhere, this is just going up as we drew it here. This is equal to 1. This is equal to the unit weight. As someone very correctly said here, the difference between a gas and a liquid is that gas is compressible. So as you go further up in the atmosphere, it gets thinner. You know that because you have to use oxygen tanks. And I think it's not because you need to use oxygen instead of, 10% oxygen, 90% nitrogen, although that helps if you're going to carry something, you might as well carry pure oxygen. It's the fact that the air is thinner, it's less dense, and so if it's present in the same proportions of oxygen and nitrogen, every breath you bring in has less fluid in it because it's less dense. And so that's the issue. The density changes as you go up. And so this would predict, if we use the constant magnitude of this unit weight, even though this expression is absolutely true, it would say that we're in a vacuum. And if we're in a vacuum, not only could you not breathe, then also your body would explode, right? Because you have a certain fluid pressure inside. That's why people wear spacesuits, not just be able to get oxygen inside the spacesuit, but the spacesuit has to be strong enough not to have that pressure inside rupture. And if it does rupture, then I think you vaporize, basically. I'm not kidding. Check that out. Go on Wiki, figure it out. So it comes back to the fact, which I guess, we have to be careful about using this issue of being able to look at water and the atmosphere. And so what we need to do is to be able to use this judiciously and in an appropriate way. So what we'll do is, instead of deriving the appropriate expression for how pressures change within a fluid only for liquids, we'll do it universally. And so what we can do now is, what we will do now, is we look at an accelerating fluid. Fluid, I guess. Okay. And so what we'll do is we'll now talk about a bucket which looks a bit different. And the bucket, instead of being a nice round bucket, is a Newton bucket or a Leibniz bucket, right? The inventors of calculus. And so it's a square. We'll use a very special sign convention. We'll use the right-hand rule in this class always. X is your thumb, right hand. Y is your index finger. And Z is your longest finger. Always arranged in a orthogonal to each other. always with Z pointing upwards, your longest finger pointing upwards. And the so-called right-hand rule will give us the x direction, the y direction, and the z direction. This will be some length dx, this will be some length dy, this will be some length dz. So instead of the height of the cube, it's just a differential length that we'll apply. The cube has an area on the top. I guess on the top it would be equal to what? Dx dy in that particular face. And just like our bucket, it has a weight pulling down on it, maybe an uppercase W as the other one was. And it has one other thing attached to it, and that is we're going to give it an acceleration in the z direction. So instead of allowing it to be static, we're going to put it in a soda can, and we're going to move it upwards. Not at constant velocity, but accelerating. Right? Difference between constant velocity and accelerating is important to make that difference. And so that's the geometry that we'll choose to use. The only equation you need for this class, I think, is Newton's second law. And Newton's second law is this. Force is equal to mass times acceleration. But I write it this way because there are forces in the x direction, forces in the y direction, and forces in the z direction. Bless you. And those are equal to the mass multiplied by the accelerations in each of these directions. So this underlined is just the fact that it's a matrix that has, or a vector rather, that has 3 components. And so what we need to do then, we could apply an acceleration in the z direction, in the x direction, and the y direction. They're all perpendicular to each other, so they don't affect each other, so they're separate, as you can imagine from this. And so we can take the first one first. So why don't we take z as the first one? Forces in the z direction sum up to be the mass times the acceleration in the z direction. And I guess this would be also the sum of these forces, have to equal that. And so what else do we have? Well, we also have a fluid pressure acting on here. We also have a fluid pressure acting on the top, which can be slightly different from this fluid pressure by some amount that we'll call dP. So it's this pressure, it changes, we don't know what the amount is, but it changes by some small amount dP. And because we're going up in the z direction, we could multiply this by 1. And multiplying by 1 is this, right? This is just 1, nothing more. So our bucket now is a differential bucket. So what? We can play some little games with it to see how pressure changes as we move around. And now we can balance forces on our system. So let's look at all the forces which act in the vertical direction. So if we resolve in the z direction, what do we have? We have an area times the fluid pressure, which is this force here. We have this force acting downwards. So we'll take positive forces in the z direction. Forces have both magnitude and direction. So this is positive. This force acting down here is negative, which is going to be the area multiplied by pressure plus the change in pressure with location times location. We have the weight of this, which is acting downwards. So this will be W that will go here, which will be equal to minus the area times dz. This is just a volume, right? The volume of this. Multiplied by the density of the fluid and by gravity. So this is just W acting downwards. And this is equal to the mass times acceleration. So mass times acceleration is again the volume which is this, times density, times, instead of this acceleration due to gravity, which is what's acting downwards, plus the acceleration in the z direction. And so that's a statement of equilibrium, if you like. It's just F equals ma where we're using some components. So what can we get rid of? Well, we can get rid of the fact that this is a plus and minus, so we can get rid of this and this. I guess we could get rid of all of the a's, I think. Let's keep the a's. So what do we have? So now we have minus, just take this. Let's keep the a's actually. Minus a dz dp dz minus a dz rho g is equal to a dz rho az. And so we note that in each of these are all the same. These are the volumes. So you can think of this kind of as a force applied per unit volume, if you like. And we can cancel those out. And we end up with an expression which is what? I'm going to write it as a partial minus dp dz this is equal to unit weight minus gamma w. I'm going to take this to the other side. This is minus rho az equals 0. I'm just subtracting this onto this side. Okay? So that's an expression. If we're not accelerating, of course, then this term goes to 0. And in the case, I'm not going to write below this, I'm going to write to the side of it. So no acceleration. Then by definition, az is equal to 0. And if that's the case, then we end up with dp dz is equal to minus unit weight. So if you like, we've kind of reaffirmed the expression we had before. But what's useful about this is it's a general expression which includes now accelerations. And we've got it merely by working through it. What we could do is now we could do the same derivations for the other directions. So now we could apply an acceleration in the x direction. And we can also apply an acceleration in the y direction. And I won't belabor those, but I will write those out because they're kind of symmetric. And those would be that the rate of change of pressure in the y direction, since this term is rho g, gravity only acts in the vertical direction. It doesn't act in either x or y. So there is no influence by the self-weight. And so this term will be 0 minus rho times the acceleration in the y direction equals 0. And if we do the same in the x direction, these are usually written the other way around, but we're going through this backwards because the tough one to do is the vertical direction. This is x minus 0 minus the density. This is density multiplied by the acceleration in the x direction is equal to 0. And so those are the expressions just by resolving Newton's second law in the z direction, in the y direction, and in the x direction. And so we bit the bullet now because we'll use those. When we start talking about accelerating fluids, we'll use these expressions as they are. For now, all we need to realize that if we're talking about static fluids, then the equations that define behavior are these first ones. because this is going to be equal to 0, this is going to be equal to 0 if we choose it to be, and this is going to be equal to 0. But we'll come back to these and you'll recognize them. And so if we summarize those expressions, there are 2 relevant ones. The first one is that vertically, the change in pressure with elevation is equal to minus the unit weight. The z direction is always upwards. So remember that. And if we look horizontally, then we know that these other 2 are that the change in pressure with the x direction and the change in pressure with the y direction are both equal to 0. There's a bug crawling on my screen, but you can't see it. This is in a static fluid. Interesting enough, this is still for static fluid, even if it's accelerating. A static fluid means that within the container that you're accelerating, it's not circulating. It's static. Even though the container is moving, everything is translating with that container. So that's still a static but accelerating fluid. A static but non-accelerating fluid, I guess that's what we're looking at here. So maybe I should write that. Is that the pressure changes with this unit weight, as we said before. And this is key as well. What does this mean physically? This means as you go horizontally in any fluid, the pressure doesn't change. And so if you're sitting in a swimming pool and you think about how pressure changes with depth in that swimming pool, well, it'll vary linearly, and you go somewhere to the right of it, then wherever you are, the pressure that you measure in each case will always be the same. And that's a consequence of this. That's all this says. It says as you change elevation, dx, the pressure doesn't change. If you don't change elevation, z, and only go in the x direction or the y direction, the pressure won't change. There is no change, so, by definition. So that's an important expression for us to use. So now we can use that to be able to do our Everest example, and if you like, also our swimming pool example. Maybe the swimming pool example is the easier one of them to do first, right? So, and I think you know the answer to this, but let's do it anyway, just because we can. So, in a liquid. So, incompressible. What does incompressible mean? Yeah. Yeah. Density doesn't change. That's a fancy way of writing, right? Change in density with pressure is 0. There's no change in density as you change the pressure. But, so, it's constant. So, we can do this calculation. So, how do we want to do this? I guess we can do this way. We'll always draw it this way. We know something. We know that this is negative, right? And so we can write it at 2 points. All we're going to do is write it at 2 points. We have P1, we have P2, we have Z1, we have Z2, and what do we have? We have dP dz is equal to minus unit weight. We'll write it as a ODE because we only have one variable. We'll split it on 2 sides. We'll integrate it between these limits. Whoops. Pressure 1, bless you, at Z1, and pressure 2 at Z2. We'll do the integration. The integration gives us what? It gives us pressure. If you're trying to remember your calculus, between the limits P1 and P2 is equal to minus unit weight Z evaluated at Z1 and Z2. You substitute the limits and we get P2 minus P1 is equal to minus unit weight Z2 minus Z1. Often we want to be able to define the pressure at P2 as a function of P1, and so often we would write it as this. P2 is equal to P1 minus unit weight Z2 minus Z1. And we know that Z2 is more negative than this, so it actually changes the sign around. And we can also write this, if we use this as a height, for instance, let's call this H, which is always positive, then this is just equal to P1 plus unit weight H. And you've probably seen that expression before. So it means that if we know what P1 is, and say this might be atmospheric pressure at the top of this liquid, top of the swimming pool, then if that were the case, then this would be 100 kPa. If we're doing the calculations in gauge pressure, in absolute pressure rather, or it would be 0 if we're taking 100 kPa now as our existing pressure. And then we could calculate the magnitude of the pressure below just by multiplying unit weight by the height. And so, well, let's go down there. So what's unit weight of water? Bless you. So 1,000 kilograms per cubic meter multiplied by 9.8 meters per second. I guess it's actually 9.81, right? And if we know elevation, h is equal to 10 meters, then you can calculate that P2 is going to be equal to just the product of those, roughly 100 kPa. So if you go down 10 meters in a swimming pool, you end up with roughly the same pressure in addition to atmospheric on the surface, to atmospheric. So we know that the pressure all around us in absolute pressure is 100 kPa. If we take that as 0, as we usually do, then if you go down 10 meters, then you've added an extra 100 kPa to the pressure that you'd feel in your ears. So, sorry. Okay. So, relatively straightforward. Okay, so that's the first part done. So we made the point that this is for a liquid. Whoops. So let's do it now for Everest. So if we ring this off, then in a gas, so I guess by definition, if we want to write this in a fancy way, is that. And so we can write out the same expression again. We know that change in pressure with elevation is equal to minus unit weight, which is equal to minus rho g. We know that pressure is equal to density times RT, the ideal gas law. And so we also know that density is equal to P over RT. This is pressure, density, they look the same. And so what we can then write is that change in pressure is equal to minus rho g dz, just writing this and this by taking the dz onto the other side. We know that this can go in here, and then this would be equal to minus pressure divided by ideal gas constant and temperature, gravity, and elevation. We have pressure now exists on both sides, and so we divide through by pressure, and we get dP over P is equal to minus G over RT dz. We integrate both sides between the pressure at point 1 at elevation 1 and the pressure at point 2 at elevation 2. And if we do this, this is just a log, and so if we do that, we get, and I'll substitute the limits, we get log P2 over P1, you can check this out yourself, is equal to, this is just the integral here, which is equal to gravity, gas constant, temperature, and the integral of this between these limits, which we just did, which is going to be Z2 minus Z1. Yep, thank you. Keep on mumbling. My ears almost work. Yeah, and it's incognito, of course. It's anonymous. And so this is the expression to be able to do that. If we want to do, we could exponentiate it. In other words, we multiply by e to the x. If we do that, we end up with P2 over P1 is equal to exponential minus G over RT C2 minus C1. And so what we could do then is, if we want to calculate what P2 is, and we know P1, then we're able to do that, because we now know what the elevations would be. And in our particular geometry, if you remember, our geometry was this. This is pressure. This is a bit of a scratchy elevation. I wish I could draw straighter lines. But that's probably good enough. This is elevation, positive. This is elevation, negative. And so what we're going to do is we're going to calculate, we like to know what the P2 is at Z2 if we know what P1 is at Z1. So this will be Z1 here, and it's some magnitude. And we'd like to know what the pressure is here. Whoops, I guess I should do it here, right? That was the whole point of doing that there. This is Z2. We'd like to know what this pressure is here. So this is P1. This is P2. And I draw this merely to make a point. And the point is, that was mentioned earlier, is that we know that as we head out from this point, if I sketch this expression, I won't do the calculation, but you can check it for yourself. In terms of P2, obviously you can multiply both sides by P1 and get P1 on the right-hand side. If I sketch this expression, it is going to look like, this. Like this. And so this is the pressure profile. And the important point to note is if I can blow this up, I'm kind of running out, well, I guess I can blow it up actually. Isn't technology wonderful? is that if you look at this little differential triangle right here, and I take that out, then this differential triangle is exactly this. This is dP, this is dz, and therefore this has to be equal to, what's this? If this is 1, then this is equal to the unit weight of air. And so the point is that at this point, we definitely satisfy that dP dz is equal to the unit weight, in this case, of air. But because its density changes as you go up, it's also true here. And so all this is saying is that because this triangle looks different, it's because for a given unit here, the density of air is decreasing. It's getting thinner as you go up. And we're accommodating that because we've used the ideal gas law to be able to do that. So I guess the point from this is don't be afraid of calculus. Calculus is just the height of this bucket of weightless bucket of stuff. Instead of having a cross-sectional area and a height, it now has dx, dy, dz, and we manipulate it in some way, but all of these things have a physical interpretation. Think of the physical interpretations in this. So in summary, we know one expression. The only expression we actually needed today was this. It is always absolutely correct, always. When we want to manipulate it to be able to figure out how pressures change from one location to another, we have to accommodate the fact that this might not always be constant. It's constant in a liquid, operationally, and it's not constant in a gas, and we have to accommodate those two. And if we do, then we can calculate fluid pressures within the column of static fluid, which is what we've done today. Okay, I'll leave it at that. Thank you very much. Any questions? Hearing none, have a great day.